This is Linux Inlaws, a podcast on topics around free and open source software, any associated contraband, communism, the revolution in general, and whatever else fancies your tickle. Please note that this and other episodes may contain strong language, offensive humor, and other certainly not politically correct language. You have been warned. Our parents insisted on this disclaimer. Happy, Mum? Thus, the content is not suitable for consumption in the workplace, especially when played back on a speaker in an open plan office or similar environments. Any minors under the age of 35, or any pets, including fluffy little killer bunnies, your trusted guide dog, unless on speed, and cute T-Rexes or other associated dinosaurs. Welcome to Linux Inlaws Season 1, Episode 78. Martin, how are things?
Yeah, things are back to normal, back to work, back to
you were on vacation,
19
right?
degrees. Vacation, holiday, yes.
So where did you go to?
I went to the Netherlands.
Why?
Because it's a great place, of course.
And of course they need the money as well, right?
No, we're fine.
When you say we, you finally intend to move back there. Did the people talk some sense into you while you were there?
No, I think there's a bit of a housing shortage even in the Netherlands as well. Yes.
Okay.
Yeah.
So you're gonna stay in the kingdom for the time being anyway?
For the time being, yes. Nothing has changed for that reason. Yeah. What about yourself? How's things?
Well, it's still 28 degrees outside in downtown Frankfurt at the kind of end of August. The population has been reduced to about 2 people who still take a shower every day. The rest basically takes a shower every month or something like that.
Excellent. Glad to hear it. Yeah.
Making progress.
Store up all the heat for the winter. Yeah. Sorted.
Yeah. And by the way, I really appreciate the UK government making that second offer that actually Germans can stay for the winter in addition to Greece. It helps a lot.
I think probably Greece is more suitable temperature.
With global warming, Greta will sort it out anyway. No worries about the UK.
Yes.
But given the fact that this is not a weather podcast, never in politics, we would like to introduce to our tonight's guest, who is Simon Cross. Without further ado, Simon, why don't you introduce yourself?
Good evening. I'm Simon. I'm also in the Netherlands, actually, although many people here would claim they're actually from Limburg and not from the Netherlands.
Yes.
Okay. You sound English, though.
I'm actually South African, but
okay.
I've never really had the traditional South African accent. I've had some strange mishmash of an English accent and the South African one. Yes, and I guess I'm here to talk, all things quantum and open source, and about what some of these, very hyped up quantum computing devices are, and whether they're going to solve all of our problems. And I think particularly also about, what I do for my day job, which is working on a open source package for simulating quantum computers. So since we are still making our first quantum computers, it is helpful to be able to make pretend ones, and probably will continue to be so for some time.
Certainly cheaper as well, I imagine.
Somewhat cheaper.
Sorry, but before we go even further, the reason why we invited Simon Cross, and he's very modest tonight on today's episode, is quite straightforward. He's probably one of the most important people in the open source quantum computing world. But before we go further, Simon, you may want to, for these two listeners out in the audience who do not know what this quantum business is all about, maybe you want to shed some light on what quantum computing is and why this is so important.
Sure. So I think quantum computing as a concept really kicked off with Richard Feynman's observation that simulating quantum mechanics using a classical computer would be exponentially slow because the sort of available sort of space of states to explore, and the complexity grows exponentially with time, and thus would take a classical computer kind of exponentially long to kind of find the answer. So Feynman put forward the idea that, well, if we can't simulate quantum mechanics with classical computers, we should simulate it with quantum computers. At the time, of course, no one had any idea what a quantum computer was, other than that it somehow used the nature of quantum mechanics itself to simulate things. And then there was, I guess, a big pause. And then the idea of circuit quantum computing, which I think is what people really mean when they talk about quantum computing now in a loose sense, was developed by David Deutsch. And he proposed a circuit-based model of quantum computing was put forward. So you can imagine something a lot like a classical circuit. You have some gates, you have bits that are sent through the gates, and the gates manipulate the bits, and new bits come out the other side, and you keep going through a long process of gates until you get to the answer that you want to compute. Except that in the quantum version, you have, instead of bits, you have qubits. Perhaps we can talk a little bit about what those are a bit separately. And instead of the ordinary sort of AND and OR gates, you have quantum gates. So there's some important gates which are just kind of rotations of the single qubits, and then some gates that operate on 2 qubits. And the hope is that this new computing paradigm will allow us to kind of achieve kind of Feynman's dream of exponentially speeding up some calculations. I think there wasn't initially a lot of excitement around these quantum computers because people didn't quite know how to build them yet, and then and they didn't have, I guess, a compelling enough problem. But then when Peter Shaw developed a factoring algorithm for factoring prime numbers a lot more quickly using these circuit-based quantum computers, suddenly everyone had a real reason to care about this, because, of course, all of our public key cryptography that we use today is, a lot of it is based on factoring large prime numbers being a hard problem to solve. And if it's not a hard problem to solve, then we will need other plans. And, of course, so this put a lot of, this I think really kicked off people very seriously thinking about how to build quantum computers. And I'm not sure if we want to go further now. There's a lot more to discuss about maybe I'll say a little bit about where we are today. So.
Yeah, but before we do that, maybe for these two listeners in the audience that do not know what Feynman is all about, what quantum mechanics are all about, maybe in very layman's terms, maybe it's worth explaining what Feynman's idea was and why this is so important for today's quantum algorithms, quantum computing, and all the rest of it. And by the way, I think we're talking about the same Feynman that I dedicated my second book to, because I came across a reference where he actually said that he basically he loves doing research in nightclubs. I read this in an autobiography of his, and this is what really struck the chord. We're talking about this Richard Feynman, right?
Yes, assuming that is the famous physicist Richard Feynman.
String theory and all the rest of it, yes.
So it's shared hobby, is it, Chris?
Indeed, very much so.
And nightclubs or string theories?
Nightclubs, actually. I wouldn't go as far as string theory. Sorry, Sam. Just go ahead. Just kind of really in layman's terms, why is this so important?
Sure. Maybe I
can understand it.
Maybe I will back up a little bit and try to say a little bit about what makes, I guess, quantum mechanics different.
Please.
So in classical mechanics, actually, let's just say in like classical computing, we have 2 bits, 0 and 1. And when you look at bit 0, the outcome is always, if you look at a bit which is in the state 0, so maybe that has a high voltage, then you always read the high voltage, and so that's always kind of read to be in state 0. And maybe then the low voltage is state 1, and then if you read the low voltage, then your bit is 1. So in quantum computing, you have a similar situation for a qubit. There are also 2 outcomes. So the one outcome you can call 0, and the other one you can call 1, as before. But now, in addition to the states the state which always has outcome 0 and the state which always has outcome 1, which are, I guess, analogous to the kind of high and low level voltages we had before, you have a lot of other states which are called superpositions. And this kind of larger space of states means that in a single qubit, you can store a lot more information potentially than in 1 bit. And if you had infinite precision, you could store kind of infinitely more information, because you have a kind of uncountably infinite number of states. In fact, the states, you can picture them as the points on a sphere. So there's a sphere called the Bloch sphere, which is a very nice visual representation of the space of all possible qubit states. And then the North Pole is the state which always has outcome 0, and the South Pole is the state which always has outcome 1. And then the states in between, so what outcome do they have? If you measure them, if you measure that and you ask the question, is the outcome 0 or 1, they will always return either 0 or 1 when you measure them, but they will do it only, the other states will do it only probabilistically. So the North Pole state always returns outcome 0, and the South Pole state always returns outcome 1, but the other states will return 0 or 1 with some probability. So this infinite state space that you have that provides you with a means of doing, of at least certainly encoding a lot more information. But there's this catch that when you measure it, you still only get out 1 classical bit from the system. So the question that quantum computing attempts to address is, how can we use this bigger state space and to perform real computations while still being restricted by the fact that the outcome is always 0 or 1. Okay, so maybe that's, I guess, a little bit of an introduction. There's also, I guess, some of the difficulties and so some of the quantumness really only comes when you have multiple qubits. But I think now I want to rather switch and say something about why this is all kind of important.
Exactly. So to summarize, essentially, the speedup comes from the fact that qubits can be more than just a simple 0 or 1, but also states in between. And this is where the speedup comes from, no?
That's not exactly where the speedup comes from, but it's one of the stepping stones to where the speedup comes from.
The floor is yours. Go ahead.
So, okay, well, let's talk a little bit about, I guess, why do people care? So there are a lot of problems that we would like to solve, which are currently very expensive to solve. So, as an example, you might want to know the behavior of a complex molecule, and this is a problem in quantum chemistry, and it's encounters the difficulty of having these much larger state spaces in quantum mechanics and trying to solve it with classical supercomputers is, if your molecule is not too large, feasible, but very slow and very expensive. And if you could simulate this molecule directly in using a quantum computer, there's the hope that you'll be able to do it much more cheaply. So I think perhaps maybe just to illustrate a really practical example. So currently there are, I guess, two different programming methodologies for quantum computers. The one is the circuit methodology I described, and the other one is a more direct physical encoding, which is sometimes called quantum simulation, confusingly, which people mean simulating your problem on a quantum system, and sometimes quantum annealing, which I think is a narrower but related term. And so D-Wave at the moment produce these quantum simulators, and you can buy one with 5,000 qubits called Pegasus for about $10 million. And that seems like a lot of money until you look at how much it costs to build Frontier, the current top supercomputer, and that was, I think, 600 million. So it's 60 times more expensive. And I think Frontier is costing about 30 million a year in electricity costs to run. And I suspect, I don't know for sure because I don't have access to a Pegasus machine, but I suspect there are a lot of problems in quantum chemistry that the Pegasus machine can solve more quickly than Frontier can. And that's with things we have today. So
can I just summarize that? I think what you just mentioned is that your 5,000 qubit D-Wave machine kind of has the same, in simple terms, same computational power as a high-performance computing cluster. Is that correct?
Yes. There've been the actual, I guess, sort of proofs that a quantum system can solve a problem faster than a classical system have been more limited. Maybe, but
Well, there's faster, and then there's the energy cost, I guess, that you mentioned as well.
Yes.
So,
So it's a bit unclear. I think we're sort of at a point where it's a bit unclear whether we've conclusively shown that quantum computers can outperform classical computers with some degree of certainty on certain problems. But I think also to some extent companies like D-Wave don't care about proving that kind of thing to people. They mostly probably want to prove it to their clients who are buying their machines. And I think the other thing here is that the quantum devices that we have now are, I think, in the usual way, only going to get cheaper and better for the foreseeable future, and they don't really have to get a lot better. They just, maybe say, I don't know for sure, but I think that it is already worthwhile to buy a D-Wave machine if you have a kind of problem that runs well on it.
And do you have some insight on let's say, the evolution of this? You mentioned 5,000 qubits, right? We all know the limits of transistors and the law about that one. Is there something similar with quantum? Or where are we in the evolutionary stage, I guess, is what I'm trying to say as well.
Yeah, I think we don't have something like Moore's law because the industry is a lot less mature. But I think that's also a benefit. So the challenges in scaling up quantum computers at the moment are, I guess, really maybe three kinds. So because the qubits are continually being jostled by noise, and when it's jostled by noise, it means your results are less accurate. And if your results are too inaccurate, then you can imagine if you apply operation after operation after operation, eventually you would just get kind of garbage out the other side. And you don't want that because you want an answer to your question. So improving what is, and this jostling by noise is called decoherence. And essentially decoherence, as the qubits are sort of jostled, the interaction with the environment kind of bleeds sort of information out of this confined system and into the kind of noise of the surrounding environment. So what people would like to do is create more isolated qubits, which thus can survive, can maintain their state for longer. So this is called the length of time for which a qubit can retain its state is called its decoherence time. And you kind of want to make that longer so that you can do longer and longer calculations. The second part is that you also need to perform operations on your qubits, and performing an operation requires interacting with the hardware system that you've created. And of course, you've tried very hard to isolate the system from the outside, but now you want to interact with it. So there's also, you want to be able to both perform your gates very precisely, but you also want to perform their operations quickly. And you want to perform them quickly so you can perform as many operations as possible before your qubit loses too much of its state to the environment. So there's sort of, I guess, two times here. There's how quickly you can perform a gate and how long your qubit can retain its state accurately. And then the number of gates you can perform is just the kind of the big time of how long the qubit can maintain a state divided by how long it takes to perform a gate. So you want to get long coherence times and short times to apply accurate gates. And then the last thing is that you also want the qubits to interact. And I think here this has two challenges. Typically, it's harder to make a very highly accurate gate that operates on two qubits than it is to interact with just one. And so there's that part. What was the second part? I forgot the second part. Anyway, but it's harder to make
Interaction
accurate
with the outside world?
Sorry?
Interaction with the outside world?
Yes, I don't think that was the point that I wanted to make. But the two qubit gates are more difficult to make, and they are vitally important to making the quantum computers faster than classical computers. So these are, I guess, these are the challenges for what I wanted to say about the two qubit gates. The other challenge is making it so that you can connect any qubit to any other qubit with a gate is quite tricky. We're sort of used to in classical computing now, we are used to, like, all of our bits are stored in RAM, and when we need a bit, it just gets copied out and put through the processor, and we've performed the operation. We can pull any two bits from memory, perform an operation on them, get out the result. In quantum computing, there is a very significant challenge, which is that you cannot copy a qubit's value without destroying it. This was proved, I think, by Jurek and a few others. It was actually maybe proved a few times actually over the history of quantum mechanics, maybe even from as early as the 1930s, but I think it was first understood as an important result maybe only as late as the 1970s, or even early 1980s, I'm not sure.
That goes back to the old adage of a box, a cat, and the guy called Schrödinger, right? If I was correct. So
correct.
essentially, sorry for the non-physicians among us, the idea is basically if you have a quantum system, you can only observe the state by actually modifying that quantum system. And the idea that Schrödinger, one of the most important quantum physicists, if my memory is correct, of the 20th century, used essentially you have a cat in a box. But correct me if I'm wrong, Simon, you can only determine if the cat is dead or not by looking into the box. And imagine the cat is in a state between being alive and dead, essentially. But by opening the box, you actually determine the state of the cat. And that's exactly, I reckon, the same thing with quantum computing, where you basically want to copy, actually, you want to assess a state of qubit. But while doing so, you actually modify the state of the qubit as such.
Yes, exactly. The no cloning theorem goes one step further. So you're entirely correct that if you measure a quantum state, then you kind of get to see the outcome, but you've also changed the state so that it's no longer what it was. The known cloning theorem goes a bit further, which it says not only can you not clone a qubit by measurement, you also cannot clone it in any other way that uses quantum mechanics as we know it.
Okay.
So, yeah. Of course, yes. So, of course, you can also imagine instead of copying your qubits, you can move them around. And some physical systems which are used for quantum computing do actually do this. But the challenge is that when a qubit is moving, when you are moving it, it's more interacting with it, which reduces decoherence times and makes everything more challenging. So maybe coming back to the kind of big picture here, so the challenges facing quantum computers in the near future are how to make better gates, how to have longer coherence times, how to have interactions between qubits that are not close to each other. So you can imagine if you want to kind of really have even say 100 qubits which can all interact with each other, and you imagine sort of laying them out physically, say on the surface of a chip or something, you would have to have very long range connections between the two. So these are all, I guess, very exciting problems to look at. Maybe this is also a good time to say that there are at least 5 or 6 different hardware platforms that people are using to build quantum computers on top of. And each of these has their own challenges. So, for example, in superconducting qubits, the kind that IBM used, the qubits are typically laid out on a surface, and it's quite hard to get interactions between qubits that between qubits that aren't neighbors in 2D. But there's another kind of quantum computer which uses cesium atoms suspended inside a vacuum with optical tweezers, and there you can arrange the atoms that you're using as to hold the states of your qubits into arbitrary 3-dimensional patterns. And in fact, if you look at some of the papers, they make all kinds of fun shapes out of sort of 100 atoms or so, like the Eiffel Tower, or like they spell out words. So there you can get kind of 3-dimensional connections very, very naturally. The ion trap quantum computers have kind of other ways of establishing gates. Sometimes you can do a gate by sending a single, a pair of photons which are related to each other to individual qubits and getting interaction that way. So there's a lot of different lot of different physical systems, and each of them has its advantages and and challenges. And people are working on sort of all of these different things. And and I don't know exactly which one will kind of be the best in the long term, or even if there will be a single best. Maybe some will be great for certain use cases, and others will be better for other things.
There is no clear direction where which one is progressing quicker than the others right now.
So there's certainly, I guess, bigger players and smaller players. So the superconducting qubits that have, I think IBM and I think D-Wave also use a similar kind of thing, are the ones which for a long time were the furthest ahead, I think, and which I think have the most resources behind them thrown behind their development at the moment. But about maybe 2 years ago, there was a little company called...
Sorry, I'm for cutting in. But superconductivity normally means you're running the machine at very close to 0 Kelvin, as in minus 279 point something Celsius, which is very close to absolute zero.
Yes,
that, of course, presents a couple of physical challenges.
Yes.
Yes, definitely.
Not to mention energy cost.
Yes, so they're typically operating at millikelvin, so like 0.001 Kelvin above absolute zero. And to achieve this, you need multiple layers of refrigeration. So you need a biggish kind of what they call a cryostat. So you can just think of it as a freezing as a fridge. So they have a bigger fridge which cools things down a lot, and then they have a slightly smaller fridge which cools things down even more, and then an even smaller fridge, and eventually they have a tiny fridge which is holding things at say 4 millikelvin. One of the big challenges you have with these very cold temperatures is every physical connection between the tiny fridge and the outside world is a potential way for heat to get in. And anything you do inside the fridge, like if you put a classical computer inside the fridge so that it can be near your qubits, that's then a source of heat. And so building and maintaining and managing these fridges is itself a big engineering challenge. And especially, I think, to do so cheaply and reliably. I guess you run into a few problems. So one is you want this very low temperature so that you get this very unusual kind of very low temperature physics. So you get your superconductivity and you get kind of very low noise. But this also changes subtly the physics of all of the materials in there. For example, you have to also the inside of the fridge also has to be a vacuum so that any kind of stray molecules don't transfer heat kind of in and out. Some solids will kind of boil off because of the vacuum. Some things that were gases will stick to things because of the cold. So there's almost like you have to learn a whole, like the way I guess you would have to, if you're someone like me who has no real experience of kind of snow and ice, you have to sort of relearn or unlearn all of your assumptions about how substances work. The same is even more true when you're trying to work on the physics inside these tiny fridges.
So to summarize, quantum-based smartphones are probably still a few years off, I suppose.
I think we're going to continue, at least for the next decade, to continue to have a lot of big new developments and surprises and a lot of progress, but not necessarily always in the direction we expect. The hardware people that I've spoken to are largely not some. Okay, D-Wave are kind of already at 5,000, but most people are talking about making planning for 1,000 qubit quantum circuit devices. So that's kind of what people are aiming for in the short term. But before we got distracted by the cryostat, the other big player is the ion trap quantum computers. So there's a company called IonQ, who I think got bought by Honeywell, and Honeywell have a lot of manufacturing capability. Actually, no, they weren't both. Sorry, no, they're just two separate people who are both doing ion trap, I think. But the ion trap quantum computers have much higher fidelity single and 2 qubit gates. And even though they have currently fewer qubits than, say, the IBM ones, there are some senses in which they are better. So there's this kind of measurement called quantum volume, where you take the number of qubits that you can run your circuit on, and the number of gates that you can successfully run with enough fidelity, and you multiply those two together to get kind of an area which is sort of number of qubits times number of gates that you can run in succession, and anyway, that number is slightly better for ion trap quantum computers than the superconducting qubits. I might mention there's actually also a variety of slightly different superconducting qubits, and when people talk about kind of superconducting qubits informally, they usually mean a particular configuration called the transmon.
Yeah,
Yes.
I found.
Go ahead.
Yeah, the ion trap method came about fairly recently, right? And it seems to be slightly more practical in its application than the superconducting one. Is that fair to say, or would you?
No, I think that seems fairly accurate. As I mentioned, each of the, I guess, hardware platforms has its own advantages, and I think the devices that use kind of individual atoms rather than say superconducting loops, which are already kind of sort of little loops of superconducting material with some structure, being smaller is usually a help, or can be a help, because it means there's just less to interact with you. And if you're a superconducting qubit, you have a superconductor glued onto a substrate, right, like a chip of some kind. And if you have an ion trap, it's just kind of like a single atom or single ion is just trapped, like hanging in space. So it's in a very kind of it's in a very high quality vacuum, just because there's if you're the size of an atom, there's a lot of empty space around you comparatively. So the platforms that use single atoms or molecules tend to have longer decoherence times, and you have a bit less noise in them. The downside, of course, is that they're also much lighter. You can imagine there's not really much chance of you losing your computer chip, but there is a chance of you just, say, losing the atom you were working with.
Absolutely.
Yeah, and with these various traps, it is something that happens. Like atoms get ejected from the trap for various reasons, and then you have to get new ones from somewhere. Well, normally you just have like a little atomizer which sort of sprays in some new atoms when you want them. But, we've also we haven't spoken about the various photonic quantum devices at all yet. So those ones, you send photons around, say something like kind of a loop of fiber, and you send lots of photons around the loop, and you arrange to interact with them as they come flying past. There you have the great advantage that it's kind of easier to get connectivity because your connectivity is mostly about timing things correctly. So if you want to have, say, photon 1 interact with photon 10, then you do an interaction when photon 1 is flying past, and then kind of use that, and then you do the next bit of the interaction when photon 10 comes flying past. So if you can get your timing precise enough, you can do sort of more interactions between arbitrary qubits more easily. So so that's another one that people are using. There's also, I guess, kind of a more cunning plan, which is instead of using a single atom, you use, say, 2 electrons that together encode the state, and but they are kept far apart. And because it's their shared information that holds the state, it's harder to modify that shared information with noise, because you would have to interact with both one small thing, so one small electron, say, at one end of a nanowire, and another small electron at the other end of a nanowire. And there's a sort of whole, I guess, like sort of academic industry of people looking at these kinds of things. And we've also, of course, left out the whole field of quantum error correction so far, which is
Before we go there, that has been more than riveting and interesting. And people, you heard it here first, it's not that complicated to build your own quantum machine. All you need is a little bit of low temperature and huge amounts of energy. That might, the latter one, of course, might be a little bit of a problem at the moment. So, Simon, jokes aside. But before we go to the other interesting theoretical concepts, maybe now is the time to shed some more light on the practical applications. And you already mentioned cryptography. But before we go into the foundation and some other interesting open source aspects, maybe you can shed some more light on the current challenges and why, for example, Google and other big companies are so much raving about quantum computing and where it helps them, as in perceived from the outside.
Sure. I want to say one thing first, which is that probably the cheapest way to get a quantum computer to play around with is to simulate one on your laptop using a piece of classical software. So very small quantum computers you can simulate very nicely, and it's a great fun, and it's a great way to learn, because it's much easier to look inside what your simulation is doing than to look inside what is happening to these tiny devices, say, inside your cryogenic fridge.
Links will be in the show notes. But if you have a project that comes to mind immediately, probably now's the time to mention it.
So, QTAP, which I work on, I guess, is generally a toolkit for simulating such things. But I will also maybe plug, because it's kind of has a bit of a sort of a nice interface where you can see things. But one of the companies called Pascal, who do these neutral atom devices, they wrote a tool on top of QTAP for simulating their own device, and they mostly use it for calibration and designing control software for their device, and for testing out control software before they try it out. But yeah, I can give you some other links to things. Maybe even to a tutorial that I have.
Great. Yeah, so come in the show notes. Okay, moving on to the more practical application side of things.
So why are people building these things? So maybe there are two good reasons. So one I'll say. Okay, let's start with the real stuff first. We can talk about the hype in a little bit. But the two sort of, I guess, really big problems which I see people working on now are one, problems in quantum chemistry, and that includes, I mean, it's not just chemistry. It's also kind of problems in biochemistry, in drug discovery, so there's really a kind of big industry who really want to be able to answer the question of, like, what does this molecule do, or how do these two molecules interact? So there's that side, and the other side, I think, where quantum computers are already starting to kind of show their value is in various kinds of logistics. So you can imagine that you have some very complicated, say, process, maybe as simple as trucks moving around, but probably probably not quite that hands-on, that you want to solve, and these problems get very challenging very fast, and because they're optimization problems, they're something which sometimes quantum computers are, or at least these kind of quantum simulators are very natural tools for using to solve. And I think part of the reason that the big companies are chasing this is that it's not so much that they know it's going to succeed, but they know the potential is huge. I mean, we've already kind of, as we discussed, sort of, it's kind of probably right now 60 times cheaper to get a D-Wave machine for certain problems than to get a classical machine, which answers the same problems. And that's quite a big thing. And I think that's why these big companies care. And you can imagine that if you're someone like IBM or Google or Microsoft, having kind of a small startup come along and offer kind of your biggest users a competing product that's 1/60th of the cost, you might care about that a lot. I think the other side, and I can't tell you what happens really deep inside IBM and inside D-Wave, but all of this, I guess, work to build these quantum computers is generating a much deeper understanding of the quantum mechanics of these kinds of systems. So, I mean, if you had gone to one of the founders of quantum mechanics and say, like, hey, I can hold like 100 atoms in space and kind of exactly manipulate all of their energy states, minds would have been blown. So I think there are also there's a lot of kind of, I guess, understanding that is generating kind of things which are not what are necessarily the things with hype behind them. So there's a company called kind of Alpine Quantum Technologies, so AQT, in Innsbruck in Austria, and they make really, they make some of their own quantum devices, but they also actually just make, I guess, components for people who are building quantum devices. There's also some similar companies at Delft who are making control software and control hardware for quantum computers. So there's a lot of knowledge being built up of how these things work, and I expect that will kind of result in a lot of really amazing things that we didn't even think to have before.
And I mean, the market's already picking up on this. D-Wave floated via a SPAC in August of 2022, and they're already clocking in with a market cap of just under 860 million. Now, for a company that has floated about a month ago, this is quite interesting, given the fact that D-Wave, and correct me if I'm wrong, Simon, only does quantum annealing, not the general quantum mechanics, as in quantum computing. They just focus on a particular type of algorithm that can be addressed by quantum annealing.
I think that's largely correct. I mean, I have seen on their website that now they do talk about doing quantum circuits, and I think I've even sort of seen some small examples, but definitely historically they were focused on quantum annealing, and that is still their strength, and I'm pretty sure a large fraction of the problems that their machines are solving kind of use that technique.
Sorry, I'm of course referring to D-Wave 2 and D-Wave 2X. as in their previous models. I have been out of touch. I have been a little bit out of touch with the market for the last couple of months, so there may have been something new in the wake of the IPO. But changing tack a little bit.
Maybe just on the topic, yes. I wanted to say, I think 2022 has been the year where quantum kind of computing, whether you mean circuit computing or annealing, has really become, I guess, a real thing. With the European HPC centers, also just like the Jülich supercomputer, which is just across the border in Germany, I think is getting one of the first kind of quantum computers at an HPC center that is being bought, I guess, to start solving real problems with. So, yeah, it really has felt like a bit of a watershed year for the quantum annealing side.
Moving on now to the open source angle, maybe you can share a little bit about insight of yours about something called the Quantum Open Source Foundation. If memory serves correct, that would be the name, and what you're doing there and why this is so important.
So I'm not I'm not part of the Quantum Open Source Foundation other than being on their Slack channel. But there's a lot of work happening in the quantum open source space. So the project that I work on, QTIP, one of the core maintainers, Nathan Shumner, who was one of the core maintainers of QTIP and is now still one of the admin team, but more at a direction setting level. He is also part of this thing called the Unitary Fund, which is a micro grant fund and community set up specifically for funding and, I guess, assisting open source projects in the quantum computing space. And because of the connection with Nathan, QTIP was one of the kind of first projects that was brought into the Unitary Fund. And they have a very active Discord server, and they give microgrants to people who propose interesting projects. And the process is actually very lightweight. So regularly people do make small proposals and implement them. And I think they also just have you can apply anytime. I don't think you have to wait for particular windows or anything. So there really are now a lot in addition. So there's a lot of open source software that is being used and developed within the quantum computing space. I know the Python stuff best because Python has been my primary language for a while. So probably the one that people know most is Qiskit. I would say Qiskit is kind of open source in the sense that it's released under the Apache 2 license, but the kind of all of the development is done inside IBM, and there isn't. Well, you can join sort of the IBM community, but you can't become I'm not actually quite sure how easy it is to become a significant contributor other than by joining IBM. But their software now covers kind of a large part of the, I guess, quantum computing stack. But there's also there also is a lot of other software. So Google has a thing called Cirq, which is also open, but managed by Google. There's a smaller company called Xanadu in Canada, in Toronto, I think, who make a whole bunch of open source tools, partly for their photonic quantum computer, but also for this thing called quantum machine learning, which combines the ideas of quantum computing and machine learning, and I guess tries to make sort of a paradigm in where you use both. My personal view is that's probably throwing too much complexity kind of into one thing to be particularly useful right now. But I could easily be wrong, and I'm sure that even if it's too much complexity right now, it will be kind of a really big practical thing at some point in the future.
I mean, even smaller companies like this corner shop called Microsoft are putting significant amounts of cash into this in terms of developer resources. For example, needless to say, of course, it's a cloud plug, but you can get something called Q#. And of course, the correlated quantum development kit, which, funny enough, runs on Azure. Needless to say, I reckon for the time being, this would be a simulation, because I don't think that actually you can get quantum resources in Azure already, but of course I stand to be corrected.
Yes, I don't know of any publicly available or publicly accessible, let's say, Microsoft hardware that you can run on, but they have also they are still working on their own hardware. I believe that they're pursuing these things called topological qubits, which are what I kind of described a bit earlier, where you have the kind of true state is spread between, say, a few different, say, electrons or atoms, and that helps you prevent it from decohering. I don't know how much progress they've made. Maybe I'll say that it was perhaps quite an ambitious plan. But that's all I kind of really know about at the moment. But they do also do a lot of other software. I think they're one of the companies who are working on this thing called QIR, which stands for the Quantum Intermediate Representation, which is a kind of, let's call it an assembly language, which can run both classical and quantum code together. So the idea there is you might want to interleave some classical and quantum operations. So, for example, you might want to perform a measurement on your quantum state, and then depending on the results, apply either kind of one gate or another gate next. So QIR is kind of designed to do this. It's perhaps a little bit over-engineered for my taste. So it was built on top of LLVM, this compiler's intermediate representation. And at least as a non-expert outsider for me, this all looks very complicated. Previously there was a simpler assembly language just called Quantum Assembler, or QASM, which was much more readable and understandable. You could just, if you can read sort of some lines which say, like, apply, say, this gate to qubit 0 and qubit 1, then you could just kind of read the quantum assembler quite nicely. But anyway, the QIR is more ambitious, and it seems that a bunch of people from Microsoft are involved with it. And I think, and I think it's even, you can compile Q# programs to QIR already or something. I don't know. Maybe the plan is that if they can compile to QIR, then they can run their Q# programs on other people's hardware easily. Maybe I should mention that NVIDIA have also been doing a lot of work in the quantum space. So I think about a year ago, they released Q Quantum, which is sort of like CUDA, but for doing, I guess, quantum computing specific stuff on GPUs. And they now also seem to be positioning themselves as the classical computing that you want to use with your quantum computer. So they're putting together, I guess, an ecosystem, I assume, based around kind of their GPUs for doing, I guess, kind of combinations of classical and quantum computing, whether that's some sort of hybrid computing model or just controlling your quantum computer using a classical computer. Yeah.
Just going back to the LLVM just a little bit. the LLVM standing for the low-level virtual machine that is the
Yes.
backend for the standard Rust implementation, and is also used heavily by a phone manufacturer called Apple.
I wasn't realized that
Swift.
Apple had used
Oh, yeah.
LLVM.
Sorry, yeah, quite a few core contributors actually are on the payroll. You actually
nice.
see this because the standard C compiler that you get with something called OS actually these days is CLang, which is of course based on LLVM.
Ah, yes.
But this is just a fun fact. Okay, Simon, that has been more than interesting. Before we wrap this up, any parting thoughts on where this whole thing called quantum computing will go in the foreseeable future, given the fact that smartphones based on quantum technologies are still a few months away?
Mm-hmm. I think the safe bets are that quantum annealers are going to become a big thing for the class of problems that they're good for. And it's probably quite a wide class of problems, probably covering optimization problems from finance, some molecular simulation, and some kind of optimization from logistics. Longer term, I would expect actually to see some really big surprises. So I would not be surprised if, say, 10 years from now, the ion trap quantum computing emerged as the better platform for circuit-based quantum computing, or perhaps even something kind of more obscure that kind of isn't sort of number 2 on the list. But I would be unsurprised by a big shakeup. And I think probably for myself personally, the most encouraging thing is that I think this is also the start of really an era of quantum engineering, which extends well beyond quantum computers. And if we do manage to build good quantum simulators, they will, I guess, push this engineering forward, because the natural thing to do with a quantum computer is to simulate other quantum systems and thus learn more about building these, be able to better engineer these quantum devices. So, yeah, I expect us to kind of, over the next 20 years, really enter a world where quantum mechanics is no longer an obscure thing that physicists talk about, but is actually a technology that we use for constructing materials, for constructing antennas, for constructing computer chips. And we probably can't tell exactly what will come out of that, in the same way that we wouldn't have been able to really say when people were making the first integrated circuit that the internet would be out there, or that we would have smartphones in the way that we do now, or that, I don't know, Elon would be trying to buy Twitter or not buy Twitter, and that this would all be the fault of kind of a too highly interconnected communication network built on all of these things. So, yeah, I think it's going to be an exciting time. I think also for people who are people like younger students, or people who are just entering the field, who are a bit earlier in their career, I think it's going to be a really big, broad field. Maybe this is, I guess, the sort of like the ARPANET of the 1960s or 70s. Just it's a kind of new big thing, which will, I think, be really important, even if specific technologies don't pan out the way we thought they would.
Very interesting perspective. That has been more than insightful. Before we wrap this up, there's something that we always do as part of an episode recording. It's called the Boxes of the Week, in terms of the picks that you and other people think worth mentioning. Martin normally does recipes or some movies or strange or British TV series that he's come across. I do sometimes movies too, but also books, because I seem to be the one that reads. But jokes aside, Simon, anything goes. So why don't you start with your observation that is worth mentioning that you have come across in the last couple of weeks?
I think I will make a plug for everything written by Yoon-Ha Lee.
Okay.
And currently, she wrote Nine Fox Gambit was the first book in the series, followed by Raven's Trap.
Yeah, I haven't read it though.
I really enjoy. Sorry,
please. A teaser, please.
How do I explain it? It's a world where kind of high technology depends on mathematics and the societal wide observation of certain minor rituals. So you have spaceships where they have kind of super powerful weapons and defenses, but they only work if the people on board maintain a certain calendar and certain sort of observances, and if the ships are flying in certain formations, and you have a society built up around this. And what really makes the books amazing is that, at least for me, is that Yoon Ha Lee manages to very sort of subtly kind of just build in beautifully narrative uses of mathematical concepts. If you don't want to commit to a full novel straight away, Yoon Ha Lee's also written a lot of short stories in the universe, which are available online. You can try. I think the Battle of Candle Arc is available online, which is a snippet about one particular battle, which some of the characters are from Nine Fox Gambit are involved in.
Okay, somebody mentioned that very recently, and it's certainly on my list of things to read. That sounds like a very good hint, Sam. Thank you very much. Martin, over to you. Your parks.
Yes, since I actually had time to read, I did some reading as well.
Excellent, Martin. We're making progress. Excellent.
if not very much. No, this was a book I was given for my birthday by some good friend, and it is called Formula One Race Engineering, which is something that
Excellent.
I tend to follow. So yes, but probably slightly off topic, but yes, nonetheless a very interesting read in terms of optimizing performance with very small gains. Right, this is the kind of the premise of the book. Yeah.
You can combine quantum computing with Formula One racing. There's a company called Zapata who do some quantum computing optimization for Formula One racing. I think because they might have been bought by Andretti.
Okay.
Right. Okay.
Oh,
wow.
Links in the show notes.
Maybe, yes.
Good link, that one. Yes.
Martin, since you mentioned your birthday, you just turned 47 and a half for the third time or something, right?
21, isn't it?
I keep forgetting I'm told for that sort of thing.
Indeed,
okay,
yeah.
my pox is a twofold one. I just have read also a book called The Founders. Links will be in the show notes. It describes the origins of something called PayPal, as in how PayPal came into existence, the early days with Peter, Alan, and all the rest of them, and how eventually PayPal was bought by eBay, and the rest, of course, is history. Very, very interesting read if you're into that sort of. I'm almost tempted to say dramatization of history, but that's probably an exaggeration, all right. But it's worth a read if you have the time to kind of dive into the history of one of the leading tech companies in the fintech world about 20 plus years ago. The other box that I have is actually a movie called The Tomorrow War. Without giving too much away, it's a sci-fi caper that talks about, or that basically shows what happens if you take a strange, very hostile alien race called the humans and let it loose on some innocent planet. Sorry, of course that's the wrong way around. Let me start again. No, essentially it's about an alien race that lands in some remote part of Russia, and then all hell breaks loose. I won't give away too much, but if you're into kind of a action-packed sci-fi caper,
like a true story. Yeah.
Exactly, true story. That's probably not the one. That's probably not a one to miss. Details will be in the show notes. Simon, that has been more than interesting. Thank you very much for your time.
Thank you, Simon.
Yes.
And looking forward to having you on the show once again. This is the Linux Inlaws.
You come for the knowledge,
but stay for the madness.
Thank you for listening.
This podcast is licensed under the latest version of the Creative Commons license, type Attribution Share Alike. Credits for the intro music go to Blue Sea Roosters for their song Solid Market, to Twin Flames for their piece called The Flow, used for the segment intros, and finally to Celestial Ground for their song Sweet Justice, used by the Dark Side. You find these and other ditties licensed under CC at Jamendo, a website dedicated to liberate the music industry from choking copyright legislation and other crap concepts.